The next speaker is Raghav. He's currently an assistant professor at the Machine Learning section, Department of Computer Science of the University of Copenhagen. His research spans sustainable machine learning, medical image analysis, and graph neural networks. He holds a PhD from the University of Copenhagen and is affiliated with the Pioneer Center for AI in Denmark and the Pan-European AI Network Alice. He has also a book, Sustainable AI. Raghav, the floor is yours.
Right. Thank you, Steph, and thank you, Veronica and Theo, for the invitation. Let me try and figure out my screen. I hope you can see the screen.
Yes.
Perfect. I would like to see you all, so I'm going to move. Okay. All right. So thank you. And also thanks to the first two presenters. So quite interesting talks, which also aligns with some of the concerns that I have, which I'm hopefully going to also convey. So I'm going to be talking about the carbon footprint of medical image analysis, and then perhaps maybe present a couple of mitigation strategies. And this is work done with several collaborators, and I've already mentioned here because I tend to forget at the end of my talk. So thanks, shout out to everybody there. Yeah, so you can also check out a lot of the work that we're doing on my group's website. We call ourselves Saints Lab, which works as an acronym here. So, all right. So this is going to be my the talk's overview. I'm going to first present a little bit of motivation for, why should we be concerned about the energy and carbon footprint of deep learning AI models, and then also do a little bit of pitch for some of the tools that we have built, and then talk about mitigation in terms of what types of metrics we could use, and then show one specific instance of a trade-off that we can achieve based on one of our recent papers. Now, I think this is sufficiently established by now, but then all of these, I have the take that all of the recent progress, recent meaning over the last 10 years or so, has been because of over-parameterization, using really large models on large data sets, which translate into compute. Here's like a plot actually from OpenAI back in the day, showing the amount of compute in logarithmic scale for different classes of models. And then this trend has continued, I think, in terms of how much compute we need. It is doubling every about 6 months. And I think now maybe even if the model sizes aren't growing as much, but the amount of data that is thrown at them, that is increasing. So this compute needs are continuing. So which means it is translating into building of these hyperscale data centers, so that some of the companies are trying to find new energy sources and build nuclear power reactors to power data centers to run AI models. And I think the amount of energy that is going to be consumed by data centers, that in itself will be about 10% by 2030, based on some estimations. This is by the International Energy Agency. Now, if you ask why is this of a concern, because energy production also has corresponding carbon footprint associated with it. And this is based on a reporting from Accenture recently, where they look at the energy consumption just for AI. And then that, they say, is going to be following this particular trend here, which is pretty crazy. And if you also look at this axis, this is showing the AI data center global CO2 emissions. And by 2030, this is estimated to be about 3.5%. And currently, I think aviation as a sector has about 2.5%, just to put things into perspective. And again, these are all estimations. There are no specific, numbers for the whole sector that we can do. But what we can, look towards is look at open source models and then think of what is happening. So a lot of our work in my group, we do talk about the environmental impact, but then AI is not just, deep learning models are also not just when we, use them for whatever task. There's a really massive and involved infrastructure that is associated with it in terms of how the models are trained, which GPUs are, how are they manufactured, what happens to downstream environmental impact because of e-waste and then mining. So there's like a lot of different elements to it. But the easy thing to do as a proxy for the overall environmental impact is to perhaps focus on some of the metrics like energy consumption here. So for this, what we can do is perhaps look at some open source models and then look at what is going on there. So this is one of the general stories in my talk, which is going to be that we should look beyond standard performance metrics and then use resources as also another aspect to measure how a particular model is achieving a certain trade-off or not. So for this is basically something that I also do in the book, where I kind of come up with what I call the resource pyramid. So usually when we are talking about model complexity, it used to be, that papers would report at least the number of trainable parameters or the training time, but I think it's getting less and less, reported based on my own reading. But I think we should go beyond and then start measuring the energy consumption and carbon footprint. So these are the more environmentally cognizant metrics. So for Llama 3, for instance, if you look at it, this is a 405 billion parameter model trained on 15 trillion tokens, took about 31 million GPU hours of training. And then the corresponding energy consumption is 21 gigawatt hour, which is, I think, the Danish national energy consumption for a week or something like that. And this is the carbon footprint associated with it. So I think the motivation for the work that we do is that the resources that are going into building AI models can also contribute to their environmental impact. And I think this is one of the key motivations with a lot of the work that we are presenting, that I will be talking about also. So just a shout out to some of the work that we do in my team. So if you're interested, please do go check out. We do have like work at each of these steps where how do you curate efficient data? How do you do model selection in a resource aware manner? How do you do efficient model training for deployment and such? So I will share the slides later. You can take a look at this. So going from here, I think the first detour into metrics is, as any true computer scientist would be, you cannot improve what you don't measure, which is, of course, that has problems in itself. Maybe that will be a point to discuss, because once you have metrics, we are very good at gaming them also. But right now we're at a place where we don't have metrics to take the resource consumption into account. So for that, what I would suggest is you try out our tool, Carbon Tracker. This has been around now for more than 5 years. It's open source and it's easy to install, and you can integrate it into your code, or you can just use it as a wrapper around whatever scripts you're doing, and it will generate a very mundane text log, which is measuring the time, the energy consumption, and the carbon footprint. And also it gives you, because carbon footprint is very abstract, so if you drove a car, how far would you be driving this car, type of an estimate. Now, of course, we want to use this metric, and then we've done this studies across different domains, but I do come from medical image analysis background, so I wanted to do this for understanding what we are doing in medical image analysis. So this was the paper that we presented at MICAI, I think, at 2022. I won't get into the details of this, but I will just quickly walk through what I did. In that was that we assumed how many papers had segment in their title. So there were about 143 papers, and then we assumed that if each of these papers, which were about segmentation, did a baseline experiment, which was using at that point, and I think still NN unit is a strong baseline, I would argue, for at least one 2D data set. And then I simulated some of these experiments, running it locally to measure the energy consumption. You might recognize this like 3D data here on brain and then heart segmentation. These are from the Decathlon Challenge. And then also 2D data sets. And then we tried to estimate that if we assume that every paper had run at least one baseline experiment using NNN, what would be the energy consumption? And that has a corresponding carbon footprint, which was about 2,000 kilograms CO2. This is assuming a bare minimum, right? So I don't think reviewers are happy if you just report one baseline. So, this just compounds, or even one with data set. And because MICAI had like a 30% acceptance rate, then all the other experiments that did not make it still had the actual carbon footprint. So then you estimate that. And that was about the annual carbon footprint of about 27 people from a low-income country. Of course, this was based on MICAI 2021. Now it's been 5 years. Now we live in the world of SAMs and all the other foundation models. So I'm pretty sure these trends have only gotten even more exaggerated. So given that, so you can, measure it using Carbon Tracker and then look at it, in a community like MICAI. So there is a considerable, resource footprint. But of course, we want to not just do, so the best model that you train in my team, we joke that is the model that you don't use ever, right? So because that has no cost, but we want to build AI models for healthcare. So how do we still couple these performance metrics, standard performance metrics like DICE or etc., with resource footprint? So and then we do a simple enough idea, what is known as the performance per resource unit. And we like to play with acronyms in my team, and then we call it PEPPER. We also have a challenge on as many food-related items in paper titles. So we're making progress. We have a paper called chili also, and then caramel and such. So in that regard, so performance per resource unit as a simple idea, like I said, is that you take whatever performance metric you have, and then you normalize it by a resource metric, which also lives within 0 and 1. So meaning you have normalized it between some min-max range, and then it gives you very interesting behavior, because what you have here is, for instance, if you have a performance metric in this case, which also is between 0 and 1, this can be anything, classification accuracy or DICE accuracy or one of those. Then on this, you have the normalized energy consumption. The 0 is like the minimum. It's not 0, it's normalized, meaning if you say your energy budget is like 1 watt hour, then this goes from 1 watt hour to, say, whatever upper limit you want to set. So what is interesting is that your PEPPER score, if you really want to get high, you want to get really good at your task specific metric with as few resources as possible. So this penalizes models which use exorbitantly high amounts of, or not exorbitantly, but then which use way more energy to achieve the same performance. So the PEPPER score keeps, degrading here. This is just like a very simple way to kind of account the resource metrics into your optimization. Now, there's different ways of doing this. So it is, if you have like a model which is not performant, and then it still uses a lot of energy, then it still has a low performance PEPPER score. But if you have a model which achieves comparably similar performance to another model which uses slightly less energy, then that has a better PEPPER score, which is what we would like. So you can do this for any type of metric, right? So you can, if you set your resource to be E, then you get the PEPPER E score. Then you can have it as carbon or data budget or memory budget or time, or you can talk in terms of tokens now. So any of these metrics, and then you can just plug this into your optimization. And if you're unhappy with the trade-offs that it offers, then you can have like an alpha variation. But the key idea is like, don't only look at performance, but then account the performance. And then the simplest way to do is just, something like this. You can do smarter things. Now, of course, we used this and then studied if this offered any interesting trade-offs. I think in the paper, it's mainly medical image classification on 3 different tasks. We explored from the Python imaging, PyTorch imaging library, about 131 pre-trained models. We wanted to see across spectrum 1 million to 125 million parameters. Each of these models were pre-trained on ImageNet 1K and then fine-tuned for your particular specific task. And this is sort of the whole space you have. And this is just to show that, like I said, it's between 1 million and then 120 million parameters. And then we also looked at, specifically if it's a transformer type of a model, or if it is a CNN backbone, or if it is efficient, if the publications for the related papers actually strive to do something efficient, did it, have any influence? So I think for this talk, what is interesting is like, if you used something like a pepper based on the energy, does that give you a reasonable trade-off? So I will, maybe this is not, yeah. So here is the performance measured as standard classification accuracy. So these are all for individual models, what you have, and then how it is distributed when you look at it based on the number of parameters. What you basically see is that, irrespective of if you have a small model or a really large model, the performance, depends on what tasks these are. Is like, it's not that it's obvious that the larger models are doing better, but it just seems like, there's nothing interesting happening here. But as soon as you plot something like Pepper E, what happens with the Pepper score is that it penalizes the larger models for achieving the same performance as a smaller class of models. So it just penalizes them. So then it gives you an interesting trade-off to say like, okay, now I might want to use these models all of a sudden because they are able to achieve similar performance using fewer resources. Now we do this with other metrics. So, and I know I was listening into the first talk. All of these also have standard deviations in the appendix of the paper. So I was just reporting this for the brevity of the results table over, I think, 10 repeats of each of these, the standard deviation. But anyway, so getting back into the metrics here. So these are some of the models which were striving to make things efficient. And then we measure, what is the maximum GPU memory that is used, what is the energy consumption, the time, and then what is the performance metric itself. Now, if you only looked at performance, then you would perhaps choose this model, right? Because it has a slightly higher value, but it is using the most energy for this particular task. But if you chose the model with the Pepper, what it does is it gives you the model with the best trade-off. So, it's not giving you the most energy efficient model, but it is giving you the model which is offering the best trade-off, sort of a Pareto optimal solution between energy consumption and then performance. And this trend holds across different tasks and things. Okay, so is the trade-off only between performance and efficiency? We would like to argue no, because it's more so important in medical image analysis because you have performance here on this axis, and then, I think in this talk, all of us are saying that we should just not look at performance. We need to look at other axes. What I have argued for is we should have like resource metrics here, but it also has other impacts. So for instance, like robustness or calibration or fairness. Now, this is just like a very high level pitch on what we can do with these composite metrics, because we cannot stop at only efficiency metrics, but then we need to take the joint interaction between also what it does. You can take a model which is performant and make it efficient, but then what does it do? So we use a very simple setting here for assessing what happens to fairness of models under quantization. Quantization is where you take a model which is usually trained in full precision, and then you reduce the number of bits allocated per weight. So this is a proxy for how much compute you will use, because it's then easily transferred into embedded devices, which in medical image applications can be very useful. And then we look at the bias using some standard benchmark data sets on, groups, group disparity, and then where the groups are based on either gender or skin color. Now, the goal is to offer the best trade-off between the two. And I will not maybe get into the details of this, but the idea is that you take a network and then we have a calibration phase where we compute how important a particular weight is in a neural network or groups of weights in minimizing the bias of these models. And we allocate more precision, more bits to those weights, and then fewer bits to the weights of the network which do not affect the bias as much. And I will skip this one for due to the interest of time. And then what we show is that, so here again, right? So the general story is that don't just look at average accuracy. In this case, because we are looking at fairness, we are also reporting group gap accuracy between the best performing and the worst performing groups, and then equality of opportunity, and then equality of odds. These are all metrics which give a hint into how fair a model is. Now, if you do look at a specific one, in this case, we can look at this model. The full precision model uses 32 bits. This is the proxy for resource consumption. And then you can quantize the models to bring it down to 8 or 4-bit. This is number of bits per weight. And then this has an impact on how many bit operations are done. That's for computation. And then this is, look at the performance and then what is happening to the model, general accuracy. This is just to say that you can go down from 32 bits in this specific setting to about 4 bits and then still achieve, reasonable trade-off between performance and fairness. So I would urge you, if that's interesting, then read the paper. But then to conclude, irrespective of what technology, even if it is AI for healthcare, we believe that the material costs cannot be decoupled from this. And then the current large-scale development of AI has a really large resource footprint. And then measuring and reporting energy consumption, is a very useful way of doing it. Scores like Pepper could be, interesting to consider. And I think it's also useful to use this so that we don't just, like the first speaker was saying, right? So that you're not optimizing for small differences in performance and such. So now if you take resources into account, then I think it reveals novel insights. So, so I think there's the question of access and democratization, but that we can keep it for another discussion. So try out Carbon Tracker. Thank you. And then, if you are interested, you can check out the book. The proceeds from the book are being donated to grassroots climate, movements. Yeah, thank you.